Now we will look at a method of solving quantifier free EUF formulas using SAT solvers. SAT solvers do not understand any of equality. All they know Boolean variables and disjunction and conjunction, and they input as in a CNF form. So what do? We translate every theory reasoning into a Boolean clauses, and then ask the SAT solver is it a satisfying formula or not. Let's see how we do it. So this method generally does not work, but only possible for the theories where we can bound the relevant instantiation of the theory axioms. In this particular case, that is possible, and we will see later on a proof where we show that the bounded instantiations are sufficient to prove the satisfiability of a formula. So this method of eager solving using SAT solvers is called Ackermann's reduction. Let's see what is Ackermann's reduction. So before that, we need to have a few definitions with us, which is En, and En is a function which maps terms to a new constants. Okay. So you can apply En to a formula to obtain a formula over the fresh constants. Let's see. What do I mean by that? So you may have a complex terms because of the functions, and what you do, you map them, each of these term into new function name. So new name called T1, T2, T3, T4. So once you do that, these names, fresh names, lose their internal structure, that okay, how T1, T2 are related. And only you know that they are two different names. You can encode any formula which has these terms appearing into the formula into the terms. For example, x is mapped to T3, so I am replacing x by T3. F of x is mapped, f of x is T1, so it maps to T1. So we obtain this formula. We will define something called Boolean encoder, which is again is a map between atoms that are appearing in the formula F and the fresh Boolean variables. Now, instead of looking at terms, now we are looking at atoms. So again, similarly, once you have such a map, you can take a formula F, and you can replace all the atoms by the corresponding proposed Boolean variable. Here's an example in which you have these equalities are mapped to these Boolean variables P1 and P2, and if I give you a formula to encode, then what you do, you replace these equalities by the corresponding Boolean variables. Now let's write down the algorithm for Ackermann's reduction. So the insight is that every possible way you can apply the axioms, you just apply them and turn them into a propositional formula. Let's see how you do it. Let's suppose your formula F is given to you and you want to check it's satisfiable or unsatisfiable. So first you collect all the subterms that are appearing in F. You create the encoder which maps these terms to the fresh constants. And also all possible equalities among these terms, you also define the Boolean encoder which assigns the equalities to the Boolean proposition variables. So what do? You first apply En on F and you get a formula G in terms of these terms. Then any two function applications where the head function is same, we introduce an instantiations of congruence axiom when we say that if their parameters are same, then their outcome is also same, and then you encode using terms of new terms. Now you instantiate all possible ways. You can apply transitivity. Then you try all possible ways. We can apply symmetry. Finally, once you have the formula G, this is not over Boolean variable. It has a set of equalities over fresh symbols. Now these equalities can further be applied on Boolean encoding, and we can turn this equality as a proposition value proofs. Now G prime has all the information that it needs to reason over equality. You can call a CDCL solver and check if it is satisfiable or not. Let's look at a simple example which make it very clear how this algorithm proceeds. You have a one disequality and one equality. First we collect all the terms that are appearing. So you have these three terms, and we map these three terms into three fresh symbols, call them f1, f2 and f3. So we need to apply all axioms that can be applied on these three symbols f1, f2 and f3 and create all the clauses for it. So first thing you take the input formula and translate into your encoding. So you say f1 not equal to f3 and f2 equals to f3. Now the complex terms are gone and simple symbols are left. Now we say, okay, can we apply congruence between them? Yes, you can apply. You can say that f2 and f3 are the fx and x, and if the function is applied, then you get the equality between f1 and f2. So this is one thing you can one instantiation of congruence consequence. Then we can apply transitivity rules, and then we say, okay, if f1 f2 equals and f2 f3 equals, then f1 and f3, and you can just say all combinations of these three symbols. You can say that the potentially transitivity can be applied on these three symbols. We do the Boolean encoding, and we have three kinds of equalities: f1 equals to f3, f2 equals to f3, f1 equals to f3. For each of them, we provide three Boolean variables, p1, p2 and p3, and translate these things into Boolean clauses. So first thing you do is that the not of p1 and p2. So you replace f1 equals to f3 by p1, then you get not of p1 here, and this guy gets replaced to p2. Similarly, we translate this clause to this Boolean propositional clause. Similarly, these three clauses are translated into again a Boolean proposition clauses here, which are three of them. Now G prime is a Boolean formula. Now you can call it SAT solver on this formula and check if it is unsat or sat. Since G prime is unsat, you can check yourself or run a SAT solver. Therefore, we know F is unsat. This is called Ackermann's reduction.